photon theorem and symptotic symmetry. Please start, and I'll give you a warning 5 minutes to the end. We'll have 50 minutes. Please.
Okay, thank you. Thanks, Shashi. Well, hello everyone. It's my first talk after the midnight, so it's very interesting experience that remind me of watching the European Cup or the final of US Open. So today I will talk about some new results when many particles are solved. The work is in collaboration with Zhengwen Liu from DZ, and it appears last month. Okay, I will start with some motivations, and then the main result for the multi-solved photon theory. And afterwards is the connection to asymptotic symmetries. And I will close with some remarks for the future direction. Well, the motivations are from the basically the connection between solved theorems and asymptotic symmetry. And once you have this symmetry, and you have a lot, you should have the symmetry algebra, and you need to check or in this connection or in the context of the triangle relation. So the point is how we can check this charge algebra in asymptotics. And there are several perspectives. One is from the celestial safety. I think we have already learned a lot from previous talk. So I think I'm in a very good position to proceed to show some different perspective. And I think to me it's very natural to think about the double solved theorem, because I think this double solved theorem was known, I think, even before we know the connection between asymptotic symmetry and the connection between asymptotic symmetry and solved theorems. But surprisingly, when I check the literatures, I think, as far as I know, I only find 3 papers, and they basically they are working on the interplay between the consecutive double solved graviton theorem and basically the BMS charge algebra. Well, so the problem we want to stress is they are at least there are 2 ways of taking the solved limit, the consecutive one or the simultaneous one. But the thing we want to stress is that for the consecutive double solved theorem, somehow you can consider as a you choose some special diagram. I will give more details on this point when you consider a precise procedure. Also, it's hard to really see the orders. I mean the time order. I mean, which one to be solved first and which one is afterwards. This is very hard to see from asymptotics. And also, you don't have more information than the single solved theorem from the consecutive double or multi-solved theorem. So that's the point. So here, what we want to do, we want to check if there are connections. First, if they are well-defined solved theorems for many solved particles simultaneously. And further, we want to check their connections to asymptotic symmetry. So, of course, for the charge algebra, the double solved theorem is enough. But of course, we want to know if it will be different when we have more solved particles. Okay, now I want to introduce some notations for computation of the multi-solved photon theorem. We consider an on-shell scattering amplitude with n hard external lights and m solved photons. So this you know in the beginning. So they are, I mean, for the solved limit, the m photons are at the same order. So we introduce a parameter, let's say lambda, or qi, the momentum of the photons are order lambda, and for the hard particle, their momentum p are order 1. And in the multi-soft limit, the amplitude is expected to factorize into a product of a universal way, like an operator acting on the amplitude with only hard particles, like this way. So by the way, I need to say this J, though there are only Q's in the parentheses, but it's really functions on both Q and P. So here only Q is only to denote that we have M soft photon, and the ellipses denotes the terms that are power surprised in the soft limit. Then it's very convenient to define a soft current. Basically, you extract or take out the polarization vectors and to define this soft current. And then, of course, it's very well known when you only have one soft photon. This soft current is the famous econo vectors. And also, it's very, or you can see immediately that Q mu J mu equal to 0 due to the conservation of the charge. And also, it's clear that the leading soft currents only see the contribution from the photons that emitted from the external hard lights. Then let's go to the for convenience, we define an endpoint effective vertex. So it's a sum of our possible contribution for emission of M soft photon from a single hard external light. And while in diagrams, just like a summation of all possibilities. So here I think I want to comment on the consecutive double source theorem. Suppose, let's look at this diagram. Suppose you take the second particle to be soft first, then this diagram will not contribute because the soft particle is from internal lights, not external lights. So you don't see this diagram. So that's the point when you consider consecutive ways to take soft limit, you will lose some diagrams. And then the single soft effective vertex is just an econo vertex. For the double one, there are only two possibilities, and it's just 1, 2 or 2, 1, and it's a very simple mathematical games. And interestingly, you find this effective vertex is just a product of two single vertex. Then for the once we have one particle, one soft particle, two soft particle, and then you want to check for 3 soft particle. There you have 6 diagrams, and while I think just very straightforward computation, you take the sum of all these 6 terms. Also, you can simplify the computation with the double soft results. You will get the triple soft effective vertex, and that's interestingly, it's again, it's a product of 3 single vertex. And now I think you are almost convinced that for any soft particle, it should be just a product of the single one. In the end, yes, the answer is it's like that, and you can prove this by induction. And I think it's just some straightforward computation. So, well, actually, surprisingly, we find that in the end, the simultaneous result is the same as the consecutive one. but I should say that it's just like a consequence because you missed a lot of diagrams, but in the end they cancel each other. And well, this soft effective vortex are the key ingredients to derive the full soft current. Then the single one is you just take the summation. I mean, all the possibilities. Like here, I mean, the photon emitted from all the possibility of all the hard lights, and then for the double case, you have two possibilities. I mean, the two photon emitted can emit from a single hard line or two hard lines. So there are only there will be two possibilities, and then you take the summation to select all the possibilities, and in the end you find the soft current for the double case. It's just a product of two single soft currents. And also you can already image for any soft photon case, it should be a product. And yes, our results confirm that for any point soft photon, if any point soft photon theorem is just a product of the single soft photon soft factors. And then the next step is we want to show is how this multi-soft photon theorems can be rewritten as wild identity of asymptotic symmetry. Well, let me just review a bit the single results, and we will work in the Minkowski spacetime in the retarded spherical coordinates, and z and z bar are the stereographic coordinates. And here we only focus on the future now infinity, and all the rest can be repeat on the past now infinity, and then you will connect the two computations by antipodal identification. Okay, in this coordinates, all the any momentum q can be characterized by its energy omega and direction on the sphere, and it works for both the soft photons and the hard particles. Suppose we only consider massless hard particles. And the single salt theorem can be rewritten in the position space in this way. And this piece on the right-hand side is the soft factors. And A plus or minus is the creation or annihilation operators, and that will create the soft photon. Okay, well, then how this soft theorem can be considered as a wild identity of asymptotic symmetry. Here is in the following way. Suppose you have a symmetry, and this symmetry is generated by a charge Q, and you can write the associated wild identity. Basically, it's a consequence of the fact that Q commutes with S. Then for a spontaneously broken symmetry, since the symmetry acts on the it will not annihilate the vacuum, so it can well, so it acts nonlinearly on the states, and we formally we decompose the charge into linear and nonlinear piece. Then the wild identity will be become in this way, and it looks already very similar to the solved the solved theorem in previous page. And then we just need to specify for different series, since we only consider the solved photon theorem. So the charge for Maxwell series defined in this way, and omega is an arbitrary function on the sphere that generates the large gauge transformation in this form, and in the ratio gauge and plus a boundary condition I will give in the next page. So it's a symmetry of the asymptotic. So well, similar to the Noether theorem, if you want this chart to be conserved asymptotically, you need to have your theory. You need to solve your theory asymptotically. So I suppose all the gauge fields and the conserved current coupled to the Maxwell fields is given in theory expansion in this way. And by the way, here I turn off the ratio component of the currents using the ambiguity of the conserved current, and we think this is a consistent choice to work with the ratio gauge condition. Well, basically the only useful relation from Maxwell equation is this one, and of course you have a lot of equations for the last subleadings, but for the game we want to continue, we only need this one. And then plugging, I'll use this relation, insert to the charge, and clearly you know which piece is the linear part, which piece is a nonlinear part, because here in the linear part you only see the current, and for the nonlinear part you only see the gauge fields. Okay, well, we need to perform a stationary phase approximation for the mode expansion, and also by using the Fourier relation, this one, and a special choice of the gauge parameter, plugging everything into the charge, you will get this result. And basically, this is sorry, I have a typo here. This should be the. Oh no, sorry, no, this is correct. And this is the left-hand side of the world identity. And then we here I need to point out that we only keep the anti-holomorphic part because of the special choice of the gauge parameter. And of course, you can get the holomorphic part when you choose epsilon equal to 1 over W bar minus D bar. And for this, it's like we are only doing with half of the full series. You need to split the current into two pieces. Otherwise, you need an extra factor of 2 that arises from a proper treatment of the radiative phase space. And then for the linear part, while for simplicity, we just consider the complex scalar charge, and the current is defined in this way. You just need the standard canonical commutation relation like this one. You can get the right-hand side of the world identity in this way. And next step is just assembling the two expressions. You can just recover the solved theorems. And as I mentioned previously, that we only pay attention to the out part, and while everything can be done similarly for the in part and plus an anti-polar identification. Well, once we the next step, double case. Clearly, to recover the double solved photon theorem from we need a nested wild identity like this way. Since I mean, both Q1 or Q2 commute with S, so the crucial ingredients is just Q1 nonlinear and Q2 S. And that's the starting point, which is, of course, when you split Q2 into linear and nonlinear part, you get this one. This, by the way, this is the starting point, and we want to start from here to get the expressions that can derive the double solved photon theorem. And we need to massage this expression by the Jacobian identity among Q1 nonlinear, Q2 linear, and S, and this way. And those two B's, the second one will be 0. I will show in the next page. And for the first piece, you just need to use the fact that S commute with Q1, so you will get the final result. Okay. While in the bracket structure, I mean, basically you are considering that the action of the first generator on the second one, and while recall the expressions of the linear piece, basically you only have the current in the linear piece of the charge, so that you have Q1 commute with Q2 linear. Somehow this is a consequence of the gauge invariance of the U component of the current. And since they're only the currents in the linear piece, so they should commute. In the end, you prove that Q1 nonlinear commute with Q2 linear. And finally, you get this result, equation 34. And clearly repeat the procedure for the connection between single solved photon theorem and asymptotic symmetry twice. You can recover the double solved photon theorem from this expression. Okay, next step 3. Well, it will be there will be more computation, but I think just tedious. And again, the crucial ingredients is why is Q3 commute with S. Okay. After splitting into linear and nonlinear part, this is our starting point. And the first step is to repeat the double case, the result of the double case for Q2 nonlinear, Q3 linear, and S. You will somehow put Q2 to the right, and also replace the Q2 nonlinear by Q2 linear. And then you need to use Jacobian between Q1 nonlinear, Q3 linear, and the commutator between Q2 linear and S. And also the commutation relation between Q1 nonlinear and Q3 linear. You will somehow put the Q1 nonlinear to the right. So somehow the game from here is you put all the small numbers to the right and large numbers to the left. And the last step, we need to repeat the result of the double case between Q1 nonlinear, Q2 linear, and S. In the end, you find all nonlinear on the left-hand side and all the linears on the right-hand side. And then to recover the triple solved photon theorem, you just need to repeat the single result 3 times. And well, once we have 1, 2, and 3, and you somehow believe this should be working for any case, yes, indeed, it's true. And again, we use inductions, and suppose that the n-1 solved photon theorem can be obtained from the world identity, from this world identity. Of course, after the suspicion, and also we know how the solved theorems can be rewritten in this language. We will have a very useful relation, equation 42, and this is very crucial to derive for the unsolved photon case. And again, we start from the world identity and use the equation 42. You get this. You get equation 44, and basically you need to the next step is to put the small numbers to the very right and large numbers to the left, and also you need to repeating the procedure m times to get this final result here in this way. So this is precisely what we need to recover the multiple solved photon theorem from the world identity of asymptotic symmetries. Well, I think I'm going to first. Is there any questions or comments? Okay, let me just close with the final remark. Well, once we have control on the leading piece, and clearly we can try for the subleadings, and also we already know the connections between the subleading single solved theorems and the asymptotic symmetries. And also, I think it's a very doable work to check the non-abelian gauge theory of gravity. And well, also in the context of the triangle relation, we can think about the memory. I think I'm quite puzzled that what is the memory effect related to, let's say, for the simple case, the double solved theorems. I don't have any clue, not yet, but for sure it's very interesting and important question, I think. Okay, I'm done, and thank you.
Okay, thank you, Pujan. Thank you for this good seminar and comprehensive. Actually, let's see if there are any questions or comments from the audience.
I think I'm just going too fast. It's very late.
I'm wondering about your thoughts about the Yang-Mills case, where this is puzzled that there's an ambiguity in the double soft limit proportional to the structure constant.
Sorry, can you say it again?
In the Yang-Mills case, life becomes suddenly much more difficult because there's an ambiguity in the double soft limit proportional to the non-abelian structure constants. I'm wondering if you have any thoughts on that.
Well, we are thinking about that, but not yet with a concrete answer, not yet. But we are working on that. Maybe I can show next year in the conference, but no, sorry. Suppose I'm invited next year.
Okay. Any other questions or comments? Okay. Let me ask one question. As you know, in the Maxwell theory, we can also have magnetic type soft charges. And the question is basically whether we have similar soft theorems for the magnetic case. And if we do we have this sort of nice features like soft current factorization and so on that we discussed for the magnetic cases, and whether they are independent of the electric ones?
I think Andy has a paper on that, the magnetic contributions to the soft theorem.
But as I remember,
I do, but I never considered the double soft case.
yeah, that was the question.
Okay.
Exactly.
Okay, sorry,
So
I would think so, yes.
so you think that are they going to be, so you are saying that they are independent of the electric ones that you discussed, and the same soft current factorization also works for the magnetic case. So that's what you would expect, right?
Yes, I would expect in that way. Yeah.
Okay. So any further questions or comments? If not, we can thank Pujian again. Thank you.
Thank you.
Stop
sharing screen.
Okay. So we are ahead of